Hi, good afternoon, everyone. Welcome to join our HKIE Civil Division technical seminar titled Sustainable Construction Innovations in Low Carbon Concrete Technology, co-organized by HKIE Civil Division and the Hong Kong Polytechnic University. This afternoon we are very glad to have Professor Zhang to give us the presentation. So let me first introduce Professor first. So Professor served as an assistant professor in the Department of Civil and Environmental Engineering in the Hong Kong Polytechnic University, concurrently holding the position of Associate Director of the Research Center for Resources Engineering towards Carbon Neutrality and the Deputy Director of the PolyU 3D Concrete Robotic Printing Research Institute. Um, Professor received his Bachelor of Science degree in Civil Engineering from the University of Minnesota, followed by his Master of Engineering and PhD in Civil Engineering as well from McGill University in Canada. Professor Zhang is dedicated to addressing pressing environmental challenges through the advancement of the sustainable construction material and the technologies. So his research focuses on concrete carbonation technology, sustainable cementitious materials, and low carbon 3D concrete printing. Professor Zhang has published more than 50 SCI research articles in the top or key journals of his research field, such as automation in construction, composites part B, engineering, cement and concrete research, etc. Professor Zhang has garnered several accolades, such as the RGC Early Career Award, National High Level Overseas Young Scholar Graduate Excellence Fellowship Award, and also many different award and fellowships. Before giving the airtime to Professor, so let me introduce let me have a briefing. We will have a Q&A session after Professor John's presentation. The participant can type your questions in the Q&A box down below in the Zoom. And so we will consolidate all the questions and answer after after Professor's presentation. Without further ado, I'm handing over the stage to Professor. Professor, please.
Okay, thank you very much, Daniel, for your kind introduction. Today's talk is regarding sustainable construction and innovations in low carbon concrete technology. I will briefly introduce actually a bundle of ideas, like what we are doing, try to help out with the climate change using in the construction sector. And there's a bundle idea of what we're doing at different phases of concrete production. But before I go to the topic, since today's talk belongs to one of the PolyU CE webinar series 2024-2025, I want to take a few minutes to introduce our department. Okay, sorry about that. I'm an assistant professor at Department of Civil and Environmental Engineering, short for CEE. CE indeed received quite a lot of global recognition. Other than PolyU ranked number 54 this year in terms of QS ranking. CE also get a very good ranking over the last year. We were ranked 17 over the world based on QS ranking. And number 2 based on Shanghai ranking in terms of civil engineering and transportation science and technology, and number 2 in terms of environmental science and engineering. We do have a very strong research background. All the faculty members, we are in total 44 faculty members at CEE, and 26 of them are ranked towards top 2% scientists. So more than 50% of our faculty member belongs in this party. And in CE faculty, we have one member of the Chinese Academy of Sciences, 7 Changjiang Scholars granted by Chinese Ministry of Education, 1 fellow of the Australian Academy of Engineering and Technology, and 1 fellow of Royal Academy of Engineering in UK. Okay. Our research has been rewarded by many signature research firms, large-scale research firms such as Sim-based research team is one of the most signature research funding in Hong Kong. And Professor Ni, Professor Li, Professor Teng, and Professor Wang, they be rewarded different, we call it TRS fund, covering topics ranging from the tropical storm resilience system for coastal cities to seawater, sea sand, concrete. Okay. And since CEE is also dedicated in improving the environmental issues and mitigate the environmental issues of Hong Kong, a couple of our colleagues secured Green Tech Fund, which focusing on, for example, the volatilization of food waste and low carbon transformation of construction material using waste glass. Professor Poon also secured a lentil conservation fund focusing on the marine biodiversity. And CE also actively engage in knowledge transfer activities. That's why we secure a couple of research impact fund, which is a funding scheme focusing on knowledge transfer instead of papers. On top of papers, we are also focusing on knowledge transfer to make impact on real world. And there are a couple of RGC collaborative research funding has been secured, which is show that demonstrating CE's role in fostering collaboration in multidisciplinary area and multi-institution in Hong Kong. CE offers a diverse programs. For undergraduate programs, we provide B.Eng in civil engineering, B.Eng in environmental engineering and sustainable development. We also offer top postgraduate programs, such as Master of Science in Civil Engineering and Master of Science in Environmental Management and Engineering. And of course, we also have research postgraduate programs, such as MPhil, a master degree focusing on research, and also PhD. Okay. We do have lots of outstanding alumni, and I just want to highlight a couple of them. Professor Choi, which is the director of CNS Limited, former assistant director of buildings, and he's also the past president of Hong Kong IA. Engineering Eric Ma, former secretary for development, and Miss Grace Cobb, chairman and executive director of AEC Group, chief sustainability strategist of AEC Capital Limited. Engineering Ricky Law, the permanent secretary for development. Engineering Goldman Ho, the fellow and director of Arab, and Ricky Wong, engineer Ricky Wong, who is the head of civil engineering office of CETD. So those outstanding alumni are continuously inspiring our current students, and indeed it strengthens our community's legacy. Okay. And CE, we do have quite a lot of advanced analytical instruments. We have 30 laboratories, 2 workshops, and 1 research center in Shenzhen. Okay. And you are more than welcome to connect with CEE. We have our own website, CEE newsletters. We also have different social media channels you can follow, from Facebook to WeChat, RedNote, you name it. Okay. All right. So before I go to my real stuff, like I want to introduce why we care about reduce the carbon footprint of concrete anyway. So I want to give you some background information. So we're all aware that different human activities has been releasing CO2. right? The global CO2 emission from energy combustion industrial processes has been dramatically increased over the last few decades. So all those CO2s will work as a blanket on the planet. So it kind of reserve all the heat energy near the surface. So the mean global surface temperature last year was for the first time over 1.55 degrees C compared to the pre-industrial level. So that is 1.5 degrees C, which is a threshold set out by the Paris Agreement. So we already over that threshold for the first time. And the consequence is merely not a warning anymore. The impact of climate change already we are extensively experiencing the consequences of climate change. For example, more frequent, more impact extreme weather events such as wildfire, drought, tropical storms. That's why the Secretary of General United Nations, Mr. Antonio, said we are on a highway to climate hill, but our foot is still on the accelerator. Unfortunately, the concrete material, that is the material I'm working on, is the most used material on this planet right after water. And this single material contributes 9% of total greenhouse gas emission globally, of which 7 to 8% is from cement only. The production of 1 ton cement will consequently lead to the generation of 1 ton CO2. So this ratio, it depends on the efficiency of the cement making plant. It's ranging between 0.6 to 1.2. So 1 ton of cement will release between 0.6 tons of CO2 to 1.2 tons of CO2. So this is a range. So if we consider concrete, the single material, as a country, it will become the third largest emitter over the world, tailing only behind US and China. The dramatic amount of efforts have been made to reduce carbon footprint of concrete. But there are basically two different philosophies, two different strategies. The most common one is called passive carbon reduction. So, for example, the industry has actively integrated different low carbon ingredients in concrete material. For example, flash, GGBS, silica fume. Those are the materials that can be replaced, that can replace cement, which is the most carbon intensive ingredients in concrete. And those low carbon ingredients are actually coming from the byproducts of the industry. So they are using the byproduct to replace cement in concrete. And it turned out to be the results are very good. So those supplementary cementitious material, that's the official term of that material, short for SCM, can enhance the concrete performance. Not only reduce the carbon footprint in concrete, it also enhances the performance of the concrete. So in Hong Kong, we are promoting the usage of GGBS. And the second strategy belongs to passive carbon reduction category, is high resilience concrete. So we try to make the concrete survive longer. From a life cycle perspective, you have a concrete that can survive longer, right? From life cycle perspective, you have a low carbon concrete. Okay, so high resilience concrete is also important, especially under the scenario where we have a dynamic climate change right now. And concrete may suffer more severe condition compared to before. And another strategy is called recycling and reuse. Okay, so again, it's from a life cycle perspective. If you can reuse the demolished concrete back into the new concrete, the overall carbon footprint of the concrete will be reduced, of course. And at PolyU, we are focusing on the other category, what we call it active carbon reduction. So this well-acknowledged greenhouse gas, CO2, will work as functional agents in concrete. So it will integrate CO2, the greenhouse gas, in concrete production process. Okay, so during this process, the carbon will be permanently captured and stored in concrete, and concrete will serve as a CO2 sink. Imagine the whole city, the mega city like Hong Kong will become a mega CO2 sink. And actually each building has the potential to sequester thousands tons of CO2 into its matrix, into its material matrix. So this is called active carbon reduction. And the rationale behind active carbon reduction is the fact that although OPC, ordinary Portland cement, the production of the cement will release 8% of total isomogenic CO2, okay? But this resulting product is highly reactive to CO2 at the same time. Theoretically, cement can absorb 70% of the CO2 emission back to its matrix. So down below is a ternary diagram shows the reaction pathway. This is a very simple chemical equations, but I won't bore you more than that. But I just want to introduce cement. If it interacts with water, though this is actually the traditional way to trigger the reaction of cement, just to interact cement powder with water. We call it a hydration reaction. Okay. Hydration reaction. So C3S, C2S, those are the mineral phases in concrete in cement, will react with water, forming CSH, which is a major binding gel in concrete, calcium hydroxide and AFT. Okay. But if we let the cement to expose to CO2, okay, instead of water, we call it early age carbonation. So carbonation reaction will occur instead of hydration. C3S and C2S will convert into calcium carbonates, silica gel, etc. Okay, so it's called early age carbonation. The beauty of carbonation is the fact that even the concrete or cement has been hydrated, okay, become this phase. It still have the CO2 reactivity, CO2 reaction potential. We call it later age carbonation. So CSH will become calcium carbonates and silica gel. Calcium hydroxide will become calcium carbonates. So it makes all those equations and the chemical features of cement make it possible to make CO2 to work as different functional agents in concrete using the early age and later age CO2 reactivity. So later age is actually even the demolished concrete, the used concrete can have this CO2 or carbonation reactivity so that carbon can be captured and stored. Okay. And this circle shows basically the outline of today's talk. So starting with material, different raw materials will be developed using solid waste, okay, from the construction grave stage. For example, we will create a novel green cement using solid waste. And this green cement will have a way lower carbon footprint because we are targeting on different phase. Okay, and we will also investigate different new SCMs generated from waste as well. So like I mentioned before, SCM is a material to replace cement. Artificial aggregates will be developed, okay, will be introduced, and different functional aggregates will be introduced. We can achieve lightweight, thermal storage, and high strength using the solid waste as a raw material. Okay, then we move to the construction phase. Okay. Concrete production phase, sorry. So we use CO2 as different non-functional agents, okay, including CO2 as an activator, precursor, curing agent, etc. Then we move to construction technology. I will primarily focus on 3D concrete printing. And in this process, CO2 will also be engaged to control the rheological behavior, to control how concrete flow during the printing process. And AI will be helped to help the control of the material status automatically. Okay, so this is today's talk's outline. Okay, so starting with raw materials. So OPC is a C3S based cement. So C3S is a mineral phase, which is a major phase in OPC. So it has been developed since 1824, more than 200 years ago. And what we want to achieve, what's next, is to, instead of using a water-cured or water-active C3S based cement, we want to switch to a cementing material that is focusing on CO2 cured, CO2 triggered. So there are a couple of phases that we developed at PolyU, including CS, C2S, C3S2, and CE. So those are the major mineral phases. We call them low carbon mineral phases. The reason why they can be low carbon is that they have a lower clinker temperature. So instead of C3S that needs a temperature 40 to 50 degrees C, these phases can be synthesized below 1100 degrees C. It has a low demand on calcium. Okay, C3S basically is a 3 calcium oxide and 1 silica oxide. Okay, so the silica calcium to silica ratio is 3.1, 3 to 1 ratio. The reason why cement making can generate a lot of CO2, there are 2 reasons. The first of all, it needs high temperature. Like I mentioned, it needs 40 to 50 degrees C. It's a very high temperature. Of course, you have associated energy and associated CO2 release. But that only accounts to 30% of the overall CO2 emission from cement plant. The 70%, the rest, the 70% is from the decomposition of limestone. In order to get calcium, right? We need normally we need to burn limestone. Limestone is calcium carbonates. Okay, during high temperature process, calcium carbonates will decompose into calcium oxide, which is what we need, right? And also CO2. So the 70% of the CO2 emission from cement making process is actually originally from the decomposition of limestone. But we have a phase with lower demand on calcium, so consequently we reduce the CO2 emission from that aspect as well. Not to mention that all those phases have a strong reactivity to CO2. Okay, so we developed a series of green cement that can be cured by CO2 using solid waste as raw feeds. Okay, and this normal cementing system can achieve a very high strength, over 110 MPa, and a high carbon capture potential, 13% of uptake. So this number means 100 grams of our material can permanently sequestrate 13 grams of CO2. Okay, and so we developed an entire system to do clinker design, to do cement making. So starting with utilization, the solid waste we utilized, including incineration bottom ash, incineration flash, those types of solid waste are generated from the incineration of municipal solid waste. Hong Kong is going to have a municipal incinerator start commissioning by the end of this year or beginning of next year. So by then we're gonna have around 500 to 600 tons of IBA plus IFA generated in Hong Kong every single day. So that can be served as a precursor for cement. Recycled concrete fine. This is from the demolition waste from the fine portion of the concrete, which also rich in calcium and silicate. And also phosphor gypsum is another type of sulfate-rich material that we utilize to produce CSA cement. Okay, and we use thermodynamic modeling software such as FactSatch to do the feed design. We can predict the phase evolution under high temperature so that we can design the raw feed accordingly. And we do the mineralogical investigation by really clinkering out the cement. And then we validate our cement use macro level performance. Strength is a number 1 rule of thumb, number 1 criteria area of our clinker. Also, we tested the durability performance of our clinker and new cement as well, etc. So we did a couple of pilot demonstration in Canada. This is we developed 2 different products. Okay, so the first product is we replaced OPC completely by our green cement, and we produced several batches of full-size CMU, concrete masonry units, and we found each block, each unit is weight around 17 kilograms, can absorb 294 grams of CO2 permanently, and it well satisfy the local standards in terms of strength, density, absorption, linear shrinkage, etc. And the second application directions is to reduce green cement as an SCM to replace 15% of the OPC. Okay, and we made a pedestrian road in front of an incinerator. Okay, so we want to demonstrate that the residues from this incinerator can become a very nicely done pedestrian road. Okay, and another cementing system we are developing is we called LMC3 system. So in this system, we engaged with the redundant solvents in Hong Kong, which is the marine clay. We can calcine this marine clay. We can active the marine clay using high temperature pyrolysis. Not high, around 800 degrees C. We can see that it achieve a good reactivity. And we found that even with 70% of marine clay, 20% of our green cement, 10% of limestone, we can achieve comparable strength to the straight OPC. So this is the batch where you have 70% of marine clay inside. And you can see that the similar level of strength can be achieved. Okay. And yeah, so that is a completely waste-derived cementing system right there again. Okay, that is enough about cement. The second major ingredient in concrete is aggregate. Okay, so we utilize different solid waste to produce artificial aggregates because aggregates can be a very attractive output for solid waste because people use concrete a lot. So that can be a very good output. You utilize the IBA, stew slag, fly ash, and BS. They are typically not solid waste anymore, but we use them to enhance the strength of the artificial aggregates. And we use CO2 and different other mineralizers to enhance the performance of the artificial aggregates. And we can actually achieve different multiple functions, including lightweight. We can control the porosity of the artificial aggregates, make it into hollow. So right highlight areas are actually hollow. So we can achieve a lightweight function feature of our artificial aggregates. Also, we can achieve a thermal storage. We can produce thermal storage artificial aggregates. We use phase change material like paraffin. We put paraffin inside the artificial aggregates, and those paraffin or phase change material can absorb and release heat during the phase changing. So once it becomes it change from solid to liquid, from liquid to solid, the heat energy will be exchanged, so that it can, once it put into the concrete, it can work as a buffer, okay, for better thermal performance. And also high strength. With the help of CO2, we can achieve a quite high strength compared to the literature reviews we did. We can achieve the highest strength, which is because low strength is normally one of the primary drawback of artificial aggregates. Okay, now we move to production process. We actively engaged CO2 as different functional agents. The first function we use for CO2 is CO2 derived seeding material. We use CO2 as the precursor for activators. So we design our own reactor, and in this reactor, CO2 will be converted into calcium carbonates, different forms, okay, different crystal forms of calcium carbonates, including calcite, waterite, aragonite, amorphous calcium carbonates, and nanosilicon. So those CO2 derived seeding material will greatly enhance the hydration, enhance the reaction of concrete. And we found particularly it's effective in active GGBS OPC binary system. And the high dosage of GGBS usage in concrete always facing a challenge is the low early age strength, because the GGBS, this material kicks in normally after 28 days. Okay, but by using our reactor seeding material, we can significantly enhance the strength of GGBS incorporated concrete. For example, when we have a GGBS incorporation of 30% compared to the reference, which is straight OPC, 100% OPC, hydrated batch recorded a lower strength, but using our reactors, we can achieve a similar level of strength compared to the reference. And this trend not only this is a 3-day compressive strength. And at 28 days, we see the same trend. For example, at 50% replacement ratio, a similar level of strength can be achieved, okay, using the CO2-derived sealing material, CO2-derived activator. And we try different means to amplify or to try to control this activator. For example, we use different chelating agent, which means that it can enhance the calcium dissolution rate. These organic additives can help out to enhance the carbonation efficiency. And we found that it can not only enhance the efficiency of the carbonation, more sealing material was generated, it can also stabilize some metastable polymorph. For example, ACC and waterite, they are thermodynamically unstable in nature. So we'll convert it gradually into calcite, but using those organic additives, it can be stabilized. Okay, so the advantages of having that metastable polymorph is that the reactivity is enhanced as well because they are metastable. Also, we use ultrasound to help us out to control the particle size of the sealing material because the shock waves and high-speed jets of ultrasound can not only facilitate the ion dissolution, because of aggregation, it can control the particle size of the sealing material into nano size, into nanoscale. Okay, and once you have a smaller particle size, the surface area is higher, the reactivity of this material is also enhanced. And CO2 is also work as a rapid curing agent. We found that in a CSA and OPC system, calcium silicate aluminum, this is cement, and carbonation, actually CO2 creates a favorable condition for yeelimite hydration. Yeelimite is a major phase in CSA. We found that a strength of 15.42 MPa can be achieved for 1 minute activation. So theoretically, after 90 seconds of compaction CO2 activation, the product is ready to deliver, to ship out. Okay, that's gonna significantly reduce the damage rate of precast concrete plant, which normally ranging from 1% to 3%, which is quite a lot. Then I moved to the construction technology, construction technique. Like I mentioned before, I'm probably focusing on 3D concrete printing. So as we all aware that all the industries are transferred towards automation and digitalization, and construction seems to be quite old-fashioned and step to the past. So this is some pictures showing the scaffolding of building since 1860s all the way to 2020s. At least from the appearance, you cannot tell much differences. So we still rely on the very labor-intensive construction process of using formwork for cast concrete. So basically, it involves cast concrete, create the desired dimension or geometry of the concrete using formworks, either made by steel or wood. Then we pour concrete in, do compaction, evaporation, and then after a certain amount of curing time, we demold the formwork. Okay, so you can tell that is a complicated, labor-intensive process. And also, formwork is the #1 solid waste source for on-site construction. Okay, that's the #1 because the wood formwork cannot be reused after a couple of their duties, right? And it's kind of costly for doing formwork, particularly in a shape where you have curved shape, curved dimension, a special dimension that you will not need the formwork anymore. The cost is very high. So at PolyU, we try to take advantage of robotic arm, okay, so that a formwork-free construction can be achieved. So basically, the concrete will be pumped to the nozzle. So this is a nozzle, the nozzle right here, and concrete will be extruded out, okay, and form a layer by layer structure, okay. so that you can tell the material requirements is quite stringent, right? Compared to cast concrete, well, you have the formwork type of concrete, you have formwork to help you out with to keep the dimensional stability. But for 3D printed concrete, the material itself, the concrete, extruded concrete itself, has to have a very good green strength, so it can hold its own dimension and can bear the loading, to bear the weight from upper layers without dramatic deformation. Okay, so the common way to achieve that is to increase the cement content. So normally the cement content in printed concrete is doubled, okay, higher than cast concrete. So indeed, it can reduce the labor, speed up construction, allow greater geometric freedom. But from material perspective, okay, it's not low carbon, right? You use too much cement. So at PolyU, the first job we did is to create this low carbon printing ink. And we consist of more than 75% of low carbon ingredients, including with glass, GGDS, and CSE cement. The rest 25%, less than 25% is OPC. So I can achieve a very good pumpability, which means the concrete can be pumped to the nozzle very smoothly. Extrudability, the concrete can be extruded out without any defects. Buildability, so the concrete can be printed up to this column. We added up to 2.5 meters, so it can has a good buildability. It can be printed in a very high without significant deformation. And we test the mechanical and durability performance of this mix is very good. And CO2 is also integrated into this process. CO2, we found that CO2 can significantly change the rheology behavior of concrete. Rheology is a science to study how material flow. So basically, the concrete extruded out is like the toothpaste that you use every morning. You squeeze the toothpaste, right? You squeeze the toothpaste out. It's a similar behavior of concrete. We squeeze it out, and in the rheology is to study to investigate how much force we need to use to make this material start to flow. We call it static yield stress, and how much amount of force we need to use to maintain the material to flow. Okay, we call it dynamic yield stress. Okay, that we found that CO2 can change the rheological behavior of the concrete from the high fluidity concrete, so that the high pumpability can be satisfied, into a low fluidity concrete, while a high buildability concrete can be satisfied within 10 seconds. So it's a very effective material gases as mixture to be added into 3D concrete printing. So it overcome, if you think about it, these two properties are conflicting to each other. So we use CO2 to harmonize the pumpability and buildability. And we found that using CO2, the static yield stress can be enhanced by more than 600%. This is a similar, same mix. Well, without CO2, it can only be printed to 6 layers, but with CO2 integration, over 33 layers of concrete can be printed out. We can print way higher than that right now. Some mechanism, we try to review the mechanism behind the CO2 interaction with concrete. From rheological perspective, we found that CO2 promotes the transition of water status. It promotes the transition of free water, okay, into capillary water, gel water, and CS interlayer water significantly. Okay, and it form a size and scale, form a larger flocculation structure. Okay, so how concrete become from a how this phase change occur from a liquid phase into a solid phase, all the magic starting with the flocculation structure. Okay, and different particles were interacting and bonding together through physical and chemical interactions, and form a large, even though it's flowable, but we call it flux, and that is closely related to the water status. And CO2 can help out to significantly enhance the size and scale and strength of the flocculation. at early age of the concrete. Okay. And we also integrate AI, computer vision, into the process. So this is the schematic illustration of how concrete will be delivered to the nozzle. So first of all, I have mixing process, pumping, and to the nozzle and extrude it out. Okay, and the concrete will be printed layer by layer, right? So the time interval between the bottom layer and upper layer can be very long, ranging from 10 minutes, 5 minutes to even 20 minutes. So concrete is a time-sensitive material. Even though you want to control it, the amount of, for example, we can control the concrete status using different accelerator, retarder, etc. The amount of accelerator, for example, CO2 that you put into the concrete should be dynamically changed because the concrete is changing over the time. But of course, you cannot have someone eyeballing the concrete right here and manually change the dosage of accelerator, dosage of CO2. Even though you use quite expensive robotic arm, you cannot still rely on us to manually adjust it. It doesn't make sense. So we developed this real-time feedback operational system based on computer vision. We use this tailor-made inception ResNet algorithm to help us how to labeling the status of the material. So there's a camera right here. We'll continuously taking pictures of extruded concrete, and the picture will be labeled real time to see that if the extruded concrete either its geometry is wrong or the status of the concrete is wrong, the fluidity of the concrete if it's wrong. Okay, so we use more than 4,000 pictures to train and to validate the whole system. Over 4,000 data sets to train the algorithm to understand what is good, what was supposed to be good in terms of printed filament. Okay, and we successfully achieve a real feedback system where the material status and geometry of the filament can be automatically optimized by automatically changing the dosage of accelerator, the dosage of CO2. And so another issue of printed concrete is high shrinkage. In traditional concrete, we have the protection of the formwork, so the water evaporation from the concrete will be minimized because you have the protection of the formwork. But for printed concrete, all the surfaces are exposed to air. So you can imagine a lot of water will be evaporated through the surfaces and create shrinkage. Okay, but there's no existing methodology can measure the shrinkage. So we develop our own distributed optical fiber sensor-based method, DOFS-based method, to continuously monitor the shrinkage behavior of the concrete. So those sensors we achieve that the occurrence of the crack can be predicted, and also the severity of the crack can be linearly correlated with the experience. And those optical fiber can not only serve as an early age monitoring purposes, it can also, because it's embedded in the printed concrete, it can also work used for long-term monitoring purposes. Okay, and like I mentioned, 3D printing kind of relieve the more design freedoms. And one of the interesting projects we're working on and we're collaborating with biologists at PolyU is to print artificial reefs. So because of climate change, again, it reduce the ocean acidity. 70 to 90% of coral may vanish within the next 30 years if we don't do anything about it. And people start to use it, but because the ocean needs the structural complexity for the species to live in, people start to use concrete to make artificial reef, but the conventional cast concrete cannot provide the intrinsic structure of real coral reefs. So 3D printing concrete can help out. So those are the prototypes we printed in our lab. Particularly this one looks small, but it's a height around 2 meters. But concrete material itself it doesn't that suitable for coral reef application, even though it's a very high durability in general. The first of all, the pH value of OPC of concrete this material is quite high, it's 13. Compared to the ocean is 8.1, 8.2 level. So it has a low bioreceptivity. Okay, the whole purpose of putting artificial reef is to let more oysters, corals to settle on. Okay, and second is the concrete is susceptible and vulnerable to sulfate attack. Okay, it can lead to low durability. So at our research center, 3D Printing Research Center, we created a CO2 reactive printing material. And by using CO2 to create a calcium carbonates surfaces on the coral reefs, we can control the mineral composition, morphology, and pH. And calcium carbonates, so these minerals, are actually redundant mineral phases in ocean. So coral reefs and also oyster shell, clam shell, they're all made by calcium carbonate. So it has a fantastic bioreceptivity. And because we formed a very densified surface on the coral reefs using this mineral, the long-term durability of concrete can be enhanced. And we found that this material can actually continually sequestrating the carbon in the ocean, bicarbonates in the ocean. And we can actually achieve a blue carbon capture function of this type of artificial reef. Okay, so there are some projects we did in Hong Kong within the framework of PolyU NAMI 3D concrete robotic printing research center, short for RCC 3D. We have different type of printers. So this is the major one, the robotic art printer. So this is the primary machine we use for our daily missions. This is quite big. It can print up to 4.75 meters high, and this printing range is 2.5, if I remember correctly. Okay, and this is a gantry type printer. Okay, it has a slower printing speed, but it's more stable. So the printing area is 2 by 2 by 2 meter. This is a powder bed printer. This is more. It can achieve a more precise printing jobs. Here are demonstrating some projects. We collaborate with CDD, Housing Society, etc. in Hong Kong. So this is the very first planetary works, public projects in Hong Kong using 3D concrete printing technologies, also some columns, signs, etc. Okay. In terms of CO2 capture rate, different technologies have different capture rate. It's ranging from 1% to 33%. Okay, means in the extreme cases, in the best case scenario, 100 grams of CO2, 100 grams of cement can sequestrate 33 grams of CO2. But let's to be conservative, let's try 1%. If all the Hong Kong concrete can sequestrate 1% of CO2, it will reduce 190 milligrams of CO2 in Hong Kong. It's equivalent to plant 5 million trees every year. Globally, this number is 75 billion kilograms of CO2 and equivalent to plant 3 billion trees every year globally. So in conclusion, at PolyU, we try to integrate the passive carbon reduction with active carbon reduction strategies. By synergistic those two carbon reduction philosophies, we want to achieve carbon capture, storage, recycling and reuse, value-added products, life cycle carbon reduction, different functionalities, and enhance the automation and digitalization in construction sector, so that the vision of zero carbon emission, livable city, sustainable development that set it out in Hong Kong Climate Action Blueprint 2050 can be achieved in the near future. Okay, thank you very much.
So thank you very much for professors very excellent presentation. So we have received a few questions from the audience. So may I invite Professor to answer one by one. So the first two questions is from one audience. The first question is regarding the LCM3 concrete. How does it how that is carbonation resistant compared to that of the normal concrete? And also the second question is it refers to the comparative economic analysis of the CO2 artificial methods versus the conventional production process. So specific for the production cost and also the CO2 equivalent emission mitigation cost to assess their potential. So Professor, please.
Yeah, it's a very good question. First one, indeed, it's similar to LC3 cement, which in general has a weaker carbonation, weathering carbonation resistance because the pH is quite low, but it also has a very good, a lot of application scenarios. But you're right, like compared to general OPC, because we use a lot of waste in that particular cement, the pH is quite low. The weathering carbonation, especially in terms of protect the rebar into the concrete, is I believe is low. Although we don't have the data to support us, this is exactly this the research direction we have right now. The second question in terms of economic perspective, if I remember, if I understand the question correctly, there are many startup companies right now working on using CO2 in concrete, particularly in the area where we have the carbon credit is expensive. For example, in European countries, the carbon credits can be as high as 70 euro per ton. So they have a lot of motivation to sequester CO2 for them. From our end, we also did quite a lot of LCA and LCC study, just to make sure that indeed it's like the hypothesis for electric cars, EV. So yes, you reduce the carbon footprint by avoid use gasolines, but the electricity you generated, you consume this, you have certain amount of energy associated or carbon emission associated with that. For CO2, for utilize carbon, the CO2 needs to be collected, purified, right, and delivered to the concrete. But the thing is that right now, many industries already have a CCUS system, carbon capture utilization system, installed in their plant at their plant. But they can collect the CO2, they can purify the CO2, but they don't know what to do with it because food industry is one of the major output of CO2, but nobody want to use the CO2 in food industry, which the gas is originally from industry, flue gas. But we can give them a good option, good alternative. Why not to utilize it in concrete and you can enhance the performance of concrete at the same time.
Okay, thank you, Professor. So the next question is regarding to the tensile strength of the concrete. So in general, the tensile strength for concrete is much weaker than its conventional strength. So in some cases, the toughness is not good enough. So with the new technology also help improve or in the country weaken the mechanical performance of concrete.
Sorry, so you're asking if this technology can increase the tensile stress?
Yeah, yeah, or the other way around, weaken the mechanical performance of concrete.
In terms of mechanical performance, we pretty sure that it's enhanced. So I have to clarify carbonation. So like 10 years ago when we start working on, or more than that, when we first started working on carbonation, it's always confused with the weathering carbonation. Weathering carbonation is a durability issue for concrete, which means that the CO2 gradually ingress the concrete during its service life. It's a long-term durability issue, which is bad for rebar. But for early age carbonation, we let the concrete exposed to CO2 at early age. It can densify the surface of the concrete very rapidly. And during this process, the concrete itself can achieve a strength level um, uh, it's the same strength level of concrete at 28-day strength within 24 hours. So we shorten the 28 days strength development curve within 1 day. And of course, tensile strength is relatively weaker, but it's proportional to compressive strength. We don't see any defects. Actually, it's increased a little bit along with the enhancement of the overall compressive strength of the concrete. Will not weaken the tensile strength, that's for sure. Yeah.
Thank you, Professor. We have another question from Mr. Lam regarding the reinforcement, steel reinforcement, whether steel reinforcement is required when we have the 3D printed concrete.
That's a very good question. Right now, it's kind of hard to put reinforcement during the printing process. Actually, in Germany, they do have some technologies. They put smaller size rebar during printing, but it's always a challenge to put full size rebar to accompany with the printing process with printed concrete. So that's why the research center recently awarded new funding, RIF, try to integrate the cast concrete with printed concrete. So the whole concept is we print a formwork where we can play around with the formwork and give different functionalities. We can use topology to control the design of the framework, and so that the cast concrete can be cast inside that printed concrete. So we overcome, in that way, we overcome the rebar issue. So during the casting of the concrete, rebar can be integrated. It's similar to the traditional cast concrete, but the formwork is a permanent formwork. It's printed by it's using 3D printing technologies. And the major reason between traditional formwork and printing formwork is the fact that topology optimization can be used here. For example, when you print, when you cast a floor, like actually, it doesn't have to be all solid. Topology can help out to make several sections hollow, but still have the same structural behavior. So that is the concept we are working on so that the rebar can be used in printed concrete as well.
Yeah, thank you, Professor. So, due to the time limitation, so maybe we come to the last question. So, referring to the construction technology, the key challenges of application of the technology in mass production. So, what is the current bottleneck for the technology now, and also do you have any energy consumption or the carbon assessment comparison for the carbon capture so as to use the CO2 in the material as the concrete?
The bottleneck. Right now, there are a couple of successful commercial cases, including one of my former colleague. He's right now a quite successful entrepreneur in Canada. And but I think the bottleneck for their business is the fact that a sealed container is needed for when using CO2 as a curing agent. A sealed container is needed so that CO2 will not be released. Okay, but for us, we kind of overcome that bottleneck. Is we can generate seeding material on site using our self-designed reactor, so that this product can be applied to cast concrete as well. Another bottleneck is that I think from the commercial wise or the motivation wise, the carbon credits of right now in Asia is not that high. If in the near future, I believe it will increase for sure. But then I think the motivation of utilize CO2 will be further enhanced. Right. Sorry, then do you have a second question about
And also about the energy for the carbon capture to
oh
use the CO2 as as material to the concrete.
energy? Yes. We did do a life cycle assessment that include a very detailed life cycle assessment, including the capture of the CO2 from flue gas, purify it, deliver it, and it still make a tremendous significant carbon reduction compared to traditional OPC, because traditional concrete is quite carbon intensive. So even though we consume a quite amount, certain amount of energy to do that, but it's still uh, way more beneficial compared to traditional concrete. Yes.
Yeah. Thank you for Professor some detailed answer. So it comes to the end of the webinar. So welcome all to join us for the webinar, and thank you again, Professor Zhang, for
Thank you.
his excellent presentation and the Q&A session, providing us a lot of information regarding to the low carbon concrete technology. So thank you all again for joining us for the webinar, and hope to see you all again in the additive in the technical meeting of HKIE Civil Division or other HKIE activities. So thank you again, thank you all again, and thank you. Yeah, see you all. Bye.
Okay. Bye bye. Thank you.